Hello everyone. Welcome to the solution of LeetCode problem 633 named Unique Path 2. In this problem, we are given a matrix of n by m and we have to go from a starting position to the ending positions, or we have to go from the top left corner to the bottom right corner. But there is a restriction. That means in this grid, there are some obstacles. So we have to find in how many ways we can go from the top left corner to the bottom right corner without any obstacle. This is the simplest problem definition. Anyways, I will explain this in the algorithm section. Suppose in the first example, this is the starting position and this star denotes the ending position. There are two different ways we can go to a start position to the ending position, where one is this way and another is this way. One extra condition is that the robot, which is now presented in the starting position, can go only right side or down side. So there are only two possible directions it can work, either right or down. So we can say that in the example 1, there are only two possible ways we can reach to the final positions from the top positions. One is this, another is this. So in this case, we have to return 2. Anyways, for the second example, we have seen that there are only one possible ways so that the robot can go to the ending positions, which is this. Because this is the obstacle, so it cannot go through it. That's why there are only one possible way. So in this case, we have to return 1. I hope you understood the problem and the examples. Now let's move on to the constraint. Here, the grid length represents by m, and the first row length can be represented by n, and each of them can be in between 1 to 100. And if in any of the positions they are presented value 0, that means it has no obstacle. But if our grid in any cell contains the value 1, that means those cell is an obstacle. So we cannot go through it. I hope you understood the problem statement definition and the constraint. Now let's move on to the algorithm. Here, for the simplicity of the algorithm, we have taken the first example. According to the problem definition, our robot currently presented at these positions here. Now it can go either two direction, or move to the right or to the down. Suppose our current robot presented here right now. Now from here, it can go either down or right, but it cannot go to the downwards position because there is an obstacle. So it can only go to the right position. Now, from here, it has only one possible way, which is downwards. And from this cell, it can go into the final destination. So this is one possible way. Now again, suppose our robot currently presented in this cell. Now from this cell, it can go either right or either down. But wait, it cannot go into the right because the right cell have the obstacle. So it is not possible. That's why it is going to the downwards position. And from the downward position, it has only one possible way, which is this. And from this cell, it can go right. So we can say that there are one possible ways, another one possible way, which is this. So in total, there are two possible ways in which the robot can move to the starting position to the end position. Now, we can solve this kind of problem by using dynamic programming. At first, try to understand why this kind of problem can be solved using dynamic programming. Because in this problem, in each step, the robot has two choices. Either he can go to the downwards, or you can go to the right side. So the basic intuition is, if in any problem we have choices, then in most of the cases, this kind of problem can be solved using dynamic programming. So again, we cannot clearly say right now that this problem can be solved using dynamic programming. Anyways, one of the major criteria for a problem to be solved in dynamic programming is those problems must have some of the repetitive subproblem. Suppose, let's try to understand the problem in an easier way. Suppose in the middle cell, it has no obstacle. Suppose this obstacle is not presented right now. Now, from the starting positions, I can go right or I can go down. Now, if I go right, then the problem is, in how many distinct ways can I go from this cell to the ending cell or to the destination cell? Before that, the problem was in how many ways we can go to the destination cell from the starting cell. But now our problem reduced into in how many ways we can go from this cell to the ending cell. Anyways, from this cell, we can go either right or I can go either down. Suppose currently we are in this middle cell. It has no obstacle right now. Just assume it. Now our problem is in how many distinct ways we can go to the ending position from this cell. So it is another subproblem. Anyways, suppose from the first position, I have go to the downwards, and currently I am presenting here. And from this cell, I have two choices. Either I can go right or I can go down. If I go right, we again end up landing in the same cell, which is the middle cell. So now our problem is in how many ways I can go to the final destination cell from this middle cell. But wait, this subproblem already appeared before. That means when from the starting position, we go right and down, we have reached the middle cell. Again, when from the starting positions, we went down and go right, again, we have come to the middle cell. And the subproblem is same. In how many ways we can go to the destination cell from this middle cell. So here we can clearly see that this original problem can be divided into subproblems and it has overlapping subproblems. So we can say that this problem can be solved by using dynamic programming. The another conditions for a problem to be categorized in dynamic programming is that this problem must have some of the base cases. Now let's try to understand what are the base cases. Suppose we are currently presented in the cell or in the destination cell, and we have to reach in the destination cell. So according to the definition, there are only one possible way we can reach from the destination cell to destination cell. So it is a base case. So till now, we have found that this problem basically has a repetitive subproblem and it has base cases. So we can clearly say that this problem can be solved by using dynamic programming. And to solve this problem, we will use bottom-up DP. Now, let's use the memorization technique to solve this dynamic programming problem. Suppose from the starting positions, when we reach the destination positions, there are only one possible way in which we can go to the destination positions from the destination positions. So it is the base case. Again, for these positions, there are only one possible way. That means the robot can only go to the right positions. And for these positions also, there are only one possible ways. That means the robot can go only to the right positions. So we can say that for all of this cell, there are only one possible way for each of them to reach to the destination positions. Now, for this cell, there are only one possible way. It can go only downwards because it cannot go to the right positions because it will become out of bound. Now, for this cell, it can go to the downwards only. So, there are only one possible ways. Now, for this obstacle cell, it cannot possible that this robot can go to the destination by going through this obstacle cell. So it will return 0 because it is not possible for a path which go in between to this obstacle cell. So it is not possible. Now this obstacle cell can return 0. Now for this cell, if currently robot is presented here, it can go either right or either down. But it cannot go right because there is an obstacle, but still it is returning some value which is 0. That means we have to accumulate the value of 0 and 1, which is 1. So we can conclude that from this cell, there are only one possible way it can reach to the destination cell, which is this. One possible ways. Again, if we present into this cell, we can only go to the right positions. We cannot go downwards because if we go to the downwards position, we will face obstacles and we cannot go through the obstacle. That's why we can only go to the right positions. But this obstacle cell is already returning value 0. That means from this cell, we have to add 0 and 1, which is 1 here. So we can say that from this cell, there are only one possible way in which we can reach to the destination cell. Now, for this starting cell, we can go either right or we can go either down. And if we go right, we will find the value 1. And if we go down, we will find the value 1. So the total number of ways from this starting cell to reach to this end cell will be 1 plus 1, which is 2. Finally, 2 is the expected output of this problem. I hope you understood the algorithm. Now let's move on to the code. In this problem, the code is pretty simple. At first, we are given a function named unique path with obstacles. And the input parameter of this function is the given grid. Now, at first, we are declaring a DP array for the memorizations, and we will set each of the cell of this DP array to -1. Now, at first, we have to check whether our destination cell will contain obstacle or not. If our destination cell contains obstacle, that means we can never go to the destination cell. So in this case, we have to return 0. That means from the starting positions, there will be no unique path we can go to the destination cells if our current destination cell will be in the obstacle. If after that, we have to call a function and initial first parameter is 0 and the second parameter is 0. After that, we have to pass the input vector which is given and the size of the input vector which is n and n, or the dimension of them. The main rule of this function or this backtracking function is that if currently we are presented in the I and J cell, we have to check whether this is the destination cell or not. If current I is n minus 1 and current j is m minus 1, and our destination cell will contain the value 0. For this case, we have to return 1. It is the base case. If currently we are presented in the destination cell, that means we have to return 1. Otherwise, if our I or j will be out of bound, or our current I and j in the obstacle grid have the obstacle, so in this case, we have to return 0. That means there will be no possible way we can go to the destinations. And for the memorizations, at first we have to check whether we have visited this cell before. If our dp of ij not equal to -1, that means we have already visited this cell before. In this case, we have to simply return the value presented in this cell. Otherwise, we have to simply call the backtracking function from the right positions, which is I plus 1j, and from the downwards positions from I and j plus 1, and accumulate the value by using this plus operator and store them to the dp of ij, and finally return them. And by using this function, we will find the number of unique way we can reach to the destination cell from the starting cell. I hope the code is clear. Now let's move on to the time and space complexity analysis of this program. In this program, the time complexity is big O of n into m, because we have to visit each of the cell exactly once. So here n and m is the dimension of the input vector. So the time complexity is big O of n into m. And the space complexity is also big O of n into m, because we are taking one extra memory or two-dimensional vector of size n and m to solve this problem, or to utilize the memorization technique of dynamic programming. So we can say that the space complexity is also big O of n into m. Thank you everyone for watching this video. We will get back soon with another LeetCode solutions.